The hydrogen is taken into stage 3, where it has two transport enzymes, being NAD and FAD. NAD and FAD then bind with the hydrogen to create NADH and FADH. The NADH and FADH then travel along the electron transport chain and are split into two separate things, one being hydrogen ions, which bind into two oxygen and create H2O, and this is a waste product used as fluid and is gotten rid of via sweating. The other is hydrogen electrons, which makes 34 moles of phosphate, which is used to make 34 sets of adenosine triphosphate. The byproducts of this system are H2O, now water, CO2, oxaloacetic acid, and the enzyme used is coenzyme A. This system can last for 12 to 24 hours, creating energy, and is used during submaximal exercise. Muscle spindles are proprioceptors, meaning they detect movement in muscles and are located in skeletal muscles. Muscle spindles specifically detect muscle stretch and initiate a reflex action to resist the stretch. Every time a muscle is stretched, information is sent to the spinal cord from the muscle spindles. While this happens, secondary sensors detect information about the degree of the stretch and send the information to the central nervous system. The central nervous system then takes the information and transmits it to the motor neuron to go and contact the muscle, and results in the reduction of the stretch. During exercise, there is an increase in movement, which means there will be an increase in the detection of stretching by the muscle spindles. The muscle spindles provide sensory information about the level of intensity of the exercise being performed. This message is then sent to the central nervous system about the level of stretch that is occurring in the muscles. The central nervous system relays the information about the amount of motor units that will be required for a smooth movement. This results in you begin to move. The initial response is there being an increase in the detection by the muscle spindles of stretch. The harder or more intense the movement, the greater stretch in the muscle is, and therefore a higher amount of motor units are recruited and used. Muscle spindles and Golgi tendon organs provide sensory information about the intensity of exercise, allowing for smooth coordination movement patterns, wrote Adams et al. Golgi tendons organs are located within tendons and are sensitive to stretch. Golgi tendon organs send information to the central nervous system concerning the stretch of a muscle contraction, and together with muscle spindles allow smooth movements. When the Golgi tendon is stretched, it relays the information to the central nervous system saying how many motor units should be used. The more the body is used to steady-state exercise, the more efficient the Golgi tendon becomes at transmitting the information as it becomes muscle memory. A hypothesis is a prediction made about something with limited knowledge on the subject. There are three types of hypothesis: null, single-tailed, and two-tailed. A null hypothesis agrees with the average. For example, if you flip a coin 20 times, the null hypothesis would be a result of 10 heads and 10 tails. A two-tailed hypothesis is where the outcome has two different possibilities. For example, with flipping a coin 20 times, the result will either be more heads or more tails. This gives two predicted outcomes, making it a two-tailed hypothesis. The final is a single-tailed hypothesis, where the outcome can only be one thing. For example, again, with flipping a coin 20 times, there will be more heads than tails, and nothing else. As you can see with the heart rate from pre-exercise to 2 minutes into exercise, the participant's heart rate has taken an increase from around 76 to 142 beats per minute for Summer, and from 58 to 108 for Maximus. With both of these heart rates matching up with the normative data for heart rate during steady-state exercise. However, Josh's heart rate goes from roughly 106 to 70 beats per minute. This is off, as it means his heart rate begins to drop when exercising, meaning he was working harder before going on the bike. There may be many different reasons for this, which include the equipment not working properly, or the recording not being taken properly, or maybe he performed too intense a warm-up beforehand, which made his heart rate shoot up. But with the heart rate not matching the normative data, I'll disregard Josh's start to exercise as it is clear it has not been recorded correctly, as your heart rate should not decrease after starting exercise. Comparing Summer and Maximus's data, they both have a rise in heart rate up until around the 4th minute, before it starts to try and level out. However, Maximus, when he hits the 4th minute, his heart rate drops slightly, then rises and drops once more, and continues this pattern until the end of exercise. Summer, from the 4th minute, increases a little bit more until 10 minutes, where it then drops but rises once more around the 16th minute mark to drop until the end of exercise. Both of these lines on the graph then show that both Summer and Max are not performing steady state exercise, as they are both raising their heart rate over 180, and they are not working sub-maximally, as steady state exercise would say they should. A lot of their heart rate keeps fluctuating up and down, meaning they have not found where the heart is at its optimum for exercise and are not staying the same heart rate. For systolic blood pressure, for Maximus and Summer, both experience an increase throughout the exercise, which is what we expect to see as an overall. However, it does drop during exercise, which is unexpected. Summer experiences an increase after exercise from post 1 to post 2, where there is no data for Max, so we don't know if his blood pressure will increase for post 2. I'm disregarding Josh's data, as they only have recorded his pre-blood pressure, which is not useful for analysing anything during or after exercise. Both Max and Summer's data agree with normative data, of which the systolic blood pressure from pre increases during exercise. With diastolic blood pressure for Maximus, during exercise his diastolic blood pressure throughout ranges between 86 to 42. This could be deemed as off, as diastolic blood pressure should not change that much at exercise, let alone rise during it. Along with Summer, as her data does the same thing and ranges between 42 to 104, which for diastolic blood pressure should not be happening. So looking at the data, increasing and decreasing, it could be that the equipment was not working properly, as the normative data suggests that diastolic blood pressure should remain level, with maybe a slight drop of around 5 millimeters of mercury, but nothing as major as displayed on the graphs. As for Josh, they only got one recording, so I will disregard this data as we have no evidence of it staying level or what happens. However, Max's data agrees with the fact that diastolic blood pressure drops during exercise, but may drop too far, whereas Summer's diastolic blood pressure increases during exercise, which is the opposite of what is expected to see. Blood lactate during steady-state exercise should remain relatively level at a low number. This is because no lactic acid should be produced during aerobic exercise. Looking at the blood lactate levels of Summer and Maximus, their levels are high at a max of 17 each, which is too high to be working aerobically, and therefore steady state. However, at 18 minutes for Maximus, his lactate levels have dropped down to 9, so for the last stage of his exercise, he could have been working aerobically. Josh's blood lactate levels, although look like they are rising up, but only go to a max of 2.9, showing that throughout the exercise he's working aerobically, and therefore was most likely out of the 3 participants to be working in a steady state. O2 saturation during steady state exercise should remain above 95%, as the body has found the optimum point to supply muscles with oxygen by staying at the same rate. As shown by Maximus's graph, his O2 sat ranges from 99% to 84%, showing us that either the machine measuring O2 sat didn't get the reading properly, as it is out of place compared to the rest of the results. He also manages to stay in the 90% bracket, which is good, however needs to stay in the 95% and above to match the normative data, which then tells us he is not working at a steady state, as the blood saturation is changing, meaning the demand for oxygen keeps increasing as he works harder. Summer and Josh both look good at the start, staying relatively level, only experiencing an expected increase at the start of exercise. However, there is no more data for them, except Summer is at 96% between 20 minutes and post 1, showing us that she may have stayed at steady state for the full exercise, but with Josh we won't be able to predict. The rate of perceived exertion should go up until around the 3rd minute, where it plateaus out until the end of exercise, where it should drop back down to where it started after around 4 minutes. However, for Maximus, his RPE shoots right up to 14 after 4 minutes of exercise and reaches up to 16 during the 8th minute, which should not be happening after this. It keeps falling until exercise stops, and then a drop down more after, so the end matches the normative data. Summer's RPE goes up to 15 within 4 minutes and stays there until the 12th minute, where she starts working harder, which shouldn't happen during steady-state exercise, as they should stay at the same intensity at the 14th minute. At the 14th minute, it's raised up to 17 and then drops down until the final reading at the 20-minute mark, where it's at 14, matching the start of her exercise. Josh's RPE is shown at 4, 10, 16 and 20 minutes, and is clearly shown to increase throughout, which suggests to me that he was not working at a fully steady-state exercise when performing on the bike. The breathing rate of all three participants experienced an increase in the start of exercise. However, Maximus has a higher breathing rate than Summer and Josh. This could be linked to him working maximally for part of the test, but still follows the trend of normative data by increasing at the start and staying relatively level throughout exercise, and dropping at post-exercise. The same happens for Summer and Josh with staying with the normative data. All three of the participants fit the normative data pattern, however their breathing rate fluctuates a little bit, but this is due to them being human and not perfect models. They all match the normative data for increasing the breathing rate at the start of exercise and starting to level out around the 4th minute and staying relatively level through the exercise and then dropping straight after. However, Maximus has the highest breathing rate, which shows after exercise at post 1 his breathing rate does not drop, rather it stays level and then drops for post 2. This could be due to him working over steady state during the exercise.